Okay, I'm recording. Okay, so the velocity of a particle as a function of its position is given by this equation. If the particle is initially, now initially always means that we're looking for when t is equal to 0. So initially x is at negative 3 meters, and we want to show that when time is pi over 12, the particle is back at its origin. So let's get started. First thing we're going to do is we're going to write out our function. Vx is equal to 9 plus x squared. Now, we can rewrite the velocity function as dx over dt, because velocity is our speed, our meters per second, which means it's a unit of comparing meters with time, or distance with time. Anywho, let's write this out. Okay, so now next thing I'm going to do is I'm going to take this across. But wait, we have a problem. And that problem is what has forced this into being complex familiar. So what we're going to have to do to take this across is we're going to have to flip our fraction. So we've got dx on the bottom, then we can take the x across. So let's flip our fraction. dt over dx is equal to 1 over 9 plus x squared. Now I can take this one across. So I'm left with t is equal to the integral of 1 over 9 plus x squared dx. Now the next thing you should be thinking is, oh my god, hot tomatoes, that is looking like one of our special calculus integrals. So when I'm looking at this, I can see that this is a nice square number. I can see that that's a nice square number. So it's probably going to be, let's look. It's looking pretty close to the inverse tan function when we integrate that one. There is a problem though, because our inverse tan function is this. A over a squared plus x squared dx is equal to tan inverse 1 x over a. Okay, so the problem that we've got at the moment is that this value at the top doesn't match this value down there, but we can make that happen. So really what we've done is we've multiplied our function, this 9 plus x squared, by some constant value when it should have been 3 squared plus x squared is equal to, there should have been a 3 at the top, but instead we've got a 1. So we had to have multiplied it by something. This side should have had the 3 there, multiplied by something, we'll turn it into the 1. So if I think about just the numerators of this, I've got 3c is equal to 1, which means c is equal to 1 over 3. So when I'm rewriting this into a form that I can use, I'm going to be writing t is equal to 1 over 3. That's the constant that we've got. The integral symbol, 3 over 3 squared plus x squared dx. Okay, and now this is something nice. Now I can apply this rule. So when I integrate it, it's going to become 1 over 3 tan inverse 1 x over 3 plus c is equal to t. Okay, so now I can start doing some of my substitution to work out what c is. So I'm going to use this first fact over here. So I'm going to let t equal 0 and x equal negative 3. So now I've got 0 is equal to 1 over 3 tan inverse 1 negative 3 over 3 plus c. So all I need to do now is figure this part out. So tan inverse 1, negative 1, is negative 45 degrees. So that'll be negative pi on 4, and that's going to be multiplied by 1 over 3, plus c will be on that side. So that will give me negative pi on 12 plus c, so that means that c is equal to pi on 12, meaning that this total equation is going to be equal to t equals 1 over 3 tan inverse 1 x over 3 plus pi on 12. Okay, so next part that we have to do is we want to show that this many seconds later the particle is back at the origin. So what I'm going to be doing is I'm going to substitute in this pi on 12 and we're going to solve for x and we'll find out that x is 0, which will prove that it's back. So we're going to let t equal pi on 12. Now the reverse of this is you can make x equal 0 and prove that that's the seconds that it's going to equal to. Doesn't matter what one you do. Okay, so pi on 12 is equal to 1 on 3 tan inverse 1 x on 3 plus pi on 12. Okay, so when I bring this over, it'll cancel out that. So I'll have 0 is equal to, now when I bring this 3 across and multiply the 0, I'll still have 0. So now I've just got 0 is equal to tan inverse 1 over 3. I take the tan across, tan of 0 is equal to x on 3. So tan of 0 is 0 as well, x on 3. And then I'm finally left with x equals 0 when I take the 3 across. So therefore I have proved that it's back at its origin.